Welcome. Today we're diving into the fascinating world of graph partitioning. Imagine you have a huge network, maybe a social network, a computer system, or even a complex data structure. Managing such a large graph can be overwhelming. That's where graph partitioning comes in. This technique helps us break down a big graph into smaller, more manageable pieces called partitions or clusters. By doing so, we can analyze, process, or optimize these smaller parts much more efficiently. Let's explore how this works and why it's so important in various fields. So why do we need to partition graphs in the first place? Well, the main goal is to group together nodes that are highly connected while keeping the connections between different groups to a minimum. This makes computations faster and more efficient, especially in parallel computing and data analysis. By minimizing the number of edges between groups, we also reduce communication costs in distributed systems. Whether it's optimizing a computer network or understanding social communities, partitioning is a key step. Graph partitioning isn't just a theoretical concept, it's used in many real-world applications. In parallel computing, it helps distribute tasks efficiently across processors. In VLSI design, it's used to optimize circuit layouts. Social network analysis relies on partitioning to uncover communities, while data science uses it for clustering and pattern recognition. No matter the field, partitioning helps make sense of complex networks and improves performance. The heart of graph partitioning is the idea of clusters and edges. We want to create groups where nodes inside a group are tightly connected, but there are only a few connections between different groups. This structure makes each partition easier to analyze and process. It's like organizing a big team into smaller, focused groups that work closely together with minimal overlap. Unpopular technique is spectral partitioning. This method uses the graph, Laplacian matrix, a mathematical representation of the graph. By analyzing the smallest eigenvalues and their corresponding eigenvectors, we can find a natural way to split the graph into balanced partitions. This approach is especially useful when we want to keep the groups as even as possible, making it a favorite in many scientific and engineering applications. Let's look a bit deeper into spectral partitioning. The Laplacian matrix captures the structure of the graph. By computing its eigenvectors, especially those linked to the smallest eigenvalues, we can identify the best way to divide the graph. This method ensures that each partition is balanced and the number of edges between partitions is minimized. It's a mathematically elegant solution to a complex problem. Another common approach is K-way partitioning. Instead of just splitting the graph into two parts, K-way partitioning divides it into K different groups. This is especially useful when you need more than two clusters, like in large-scale data analysis or multiprocessor systems. The challenge is to keep all partitions balanced and minimize the edges between them, which often requires smart algorithms and heuristics. K-way partitioning uses optimization algorithms to ensure that each group is roughly the same size. This balance is crucial for applications like parallel computing, where each processor should handle a similar workload. By minimizing the number of edges between groups, the system runs more efficiently and avoids bottlenecks. Medi's algorithm is a widely used tool for graph partitioning. It's known for its efficiency and effectiveness, especially with large graphs. Medi uses a multi-level approach. It first simplifies the graph, then partitions it, and finally refines the solution to improve quality. This step-by-step process makes Medi a go-to choice in both academia and industry. Medi starts by coarsening the graph, which means it merges nodes and edges to create a simpler version. Next, it partitions this smaller graph, which is much faster and easier. Finally, it refines the partitions, making small adjustments to improve the overall result. This multi-level strategy allows Medi to handle very large and complex graphs efficiently. Recursive bisection is another powerful technique. Here, the graph is split into two parts and then each part is split again recursively until all partitions are of a manageable size. This approach is simple yet effective, especially when you need to keep breaking down a large graph into smaller and smaller pieces. Main advantage of recursive bisection is its simplicity. By repeatedly splitting the graph, you can control the size of each partition very precisely. This is especially useful in hierarchical systems or when you need to process data in stages. It's a straightforward method that works well for many practical problems. Label propagation is a unique approach to graph partitioning. In this method, each node starts with a label, and during each iteration, nodes adopt the most common label among their neighbors. This process continues until the labels stabilize, naturally forming clusters. It's a fast and intuitive way to detect communities in large networks. With label propagation, the algorithm updates each node's label based on its neighbors. Over several rounds, nodes with similar connections end up sharing the same label, forming natural clusters. This method is especially useful for large, dynamic graphs where traditional partitioning might be too slow or complex. One of the biggest benefits of graph partitioning is optimizing computations. By working with smaller subgraphs, algorithms can run faster and use less memory. This is crucial in big data applications where efficiency can make a huge difference in performance and cost. In parallel and distributed systems, communication between different parts of the system can be expensive. Graph partitioning helps by minimizing the number of edges between partitions, which means less data needs to be transferred. This leads to faster, more efficient systems and lower operational costs. Partitioning also helps us understand complex networks. By breaking a large graph into clusters, we can identify important patterns, communities, or structures that would be hard to see otherwise. This is especially valuable in social network analysis, biology, and other fields where networks are huge and intricate. Despite its benefits, graph partitioning comes with challenges. Finding the perfect balance between partition sizes and minimizing cross-group edges isn't always easy. Some graphs are highly irregular, making it tough to split them evenly. That's why researchers continue to develop new algorithms and techniques to improve partitioning results. So many partitioning methods available, how do you choose the right one? It depends on your specific needs, whether you need speed, accuracy, or scalability. Spectral methods are great for balanced splits, while MEDIS is excellent for large graphs. Label propagation is perfect for community detection. Understanding your problem helps you pick the best tool. Field of graph partitioning is always evolving. As networks grow larger and more complex, new algorithms and tools are being developed to handle these challenges. Advances in machine learning and artificial intelligence are also influencing how we approach partitioning, making it faster and more adaptive than ever before. Wrap up, graph partitioning is a powerful technique for managing and understanding large networks. Whether you're optimizing computations, reducing communication costs, or uncovering hidden patterns, partitioning plays a crucial role. With a variety of methods available, there's a solution for every problem. As technology advances, graph partitioning will only become more important in data science and beyond.